Hi, everyone. So Holger Muller from UC Berkeley. I'm going to talk about the laser faceplate for electron microscopy. And I will have an outlook slide at the end, how we can use, let's say, quantum 2.0 techniques to perhaps one day overcome the shot noise. But the laser faceplate is intended to bring biological imaging of single proteins, of lamella, to the shot noise limit. It's in 1959, Feynman gave this famous speech, "There's plenty of room at the bottom," at Caltech. And one of the things he exhorted the community, the physics community, to do is be less arrogant. Talk to me about that in 30 years. And to make the electron microscope 100 times better. Unfortunately, it didn't specify in which way he wanted to make the electron microscope 100 times better. Fortunately for us, we have Bob Glaser at Berkeley who said, let's build a laser-based faceplate. Okay, single particle cryo-electron microscopy is now the up-and-coming method to gain structural information on biological macromolecules. You can see here the number of deposited protein structures in the protein structure database as function of time. The plot stops in 2016. That was just a few years after what we call the resolution revolution, by which I mean that there are now plenty of structures with a resolution better than 6 angstrom, better than 4 angstrom, and the record these days is even better than 2 angstrom. It has to be said that these very high resolutions are only achieved by averaging hundreds of thousands of particles and only for the largest particles. The method is that a cryo-EM specimen contains purified proteins, hundreds and thousands of them in a single image. They all have different orientations. The computer can put the images of taken from different orientations together and yield a 3D reconstruction by the Fourier slice theorem, okay? And then, but this works only for single molecules of which you can have lots in a single image. How about seeing these molecules in the biological context? Well, there's an answer to that too. You take a cell, and cell is actually way too large to stick into an electron microscope. That's one of the jarring things that I had to learn while doing this project. So you take a focused ion beam mill to cut a thin lamella out of the slice, and then you can image that, and you image it in 2 or 3 degree steps under different tilt angles, and then again using the Fourier slice theorem, reconstruct a 3D structure of that lamella. Now the problem is, why is that so hard? It's so hard because the raw data looks more like the image on the right. Of course, this is plotted in a very unflattering way. You can plot it in a more flattering way. Suffice it to say, the contrast of these images is very feeble, and as a result, the signal to noise is very bad. Let's think about the physics limitations. So there's an electron beam going through the specimen, interacting with the atoms inside the specimen, right? The interaction between the electron beam and the atoms is governed by the scattering cross-sections of the atoms, which is very small for light atoms because the electron density there is small. And unfortunately, biological specimens are mostly carbon, nitrogen, oxygen, hydrogen, extremely light elements. And therefore, even at the theoretical limit, you need to average hundreds or thousands of particles to get a structure. Why don't you just keep exposing to increase the signal to noise? Because roughly 10 electrons per angstrom square begin to alter the structures that you want to know, and hundreds of electrons per angstrom square completely destroy them. So you can't just increase the dose. In practice, all the information that is generated by electron-atom interactions is not made visible on the camera, and therefore in practice, hundreds or thousands of particles aren't enough, and you need 10,000s or 100,000s. So what do you do? Let's look at the problem a little bit. So because of the weakness of the scattering cross-section, biological specimens are what's called weak phase objects. That means they hardly absorb the electron at all, and that means that a perfect image has 0 contrast, okay? what they do is phase shift the electron wave function. Okay. For the physicists here, the incoming electron beam I've written as a plane wave e to the I k z, and phase object means that the e to the I k z gets another phase factor attached to it, e to the I phi, where phi is the phase shift induced by the electron interactions with the specimens. And since the phase shift is weak, I can expand this in a Taylor series, taking only the first term. Okay, so what I'm imaging is something like 1 plus I phi, where phi is a small number. The camera doesn't see phase shifts. It sees the electron number, which is proportional to the absolute square of the wave function. And the absolute square of this wave function is exactly 1. And that's the problem we're talking about. There's no contrast. If I was able now to phase shift part of the electron beam so that the 1 in the Taylor expansion becomes an I, now I'm taking the absolute square of I plus I phi, and that, yes, and that has contrast. Okay, now I have a first order influence of the phase shift on the number of arriving electrons. How do I do that? Well, here's a simplified schematic of the electron microscope, and the 1 that was here, and that has to become an I, that represents the undiffracted part of the electron wave function. So if the electron beam goes through the specimen, part of the electron population will not be diffracted. And that comes to a sharp focus in the objective lens back focal plane. Okay. And the rest, the I phi here, is the part of the wave function that did get scattered, and that surrounds this sharp focus here. So if I have a phase shifter that could phase shift only this undiffracted part, leaving the rest alone, then I would generate phase contrast. That was invented by Fritz Zernike in the 1930s or 40s, and in biological optical microscopy, this is a method that is used so often that people don't talk about it anymore. So why is it so hard in electron microscopy? Well, it has been done. Most recently by Radoslav Danev, who put a thin carbon film in the back focal plane, and then the concentrated electron stream at the center modifies that film, charges it, damages it a little bit, so that a phase shift builds up over time. And if you expose the carbon film for a while, then you get a 90-degree phase shift. And in those moments, you can take gorgeous images plotted there. The problem is the phase shift keeps increasing until it's too large, and then you have to find a new spot on your Volta faceplate. And because of this instability, few people have used it successfully. Again, we have to take hundreds of images, ideally under the same conditions, in order to extract biology from here. So the idea is to use a laser beam as an electron phase shifter. Focus a laser beam so that the laser focus overlaps with the electron focus, use that as a phase shifter. Of course, the laser beam is also going to generate a weaker phase shift to the rest of the wave function, but that creates minor issues that I won't get into. But the main advantage is the laser beam can't get charged, it cannot suffer radiation damage. So that should be a well-controlled effect. And laser beam is also nicely predictable because it has to obey Maxwell's equations, right? The problem is the electron laser interaction is extremely weak, and so we would need 75 kilowatt of laser beam focus to 8 microns to get the required phase shift. To put that in perspective a little, on the left-hand side is the biggest welding laser that IPG Photonics will sell you. It cuts through 2-inch steel at a reasonable speed and so on. So this is really a badass laser. We'd need 7 or 8 of them, and we can't afford them. The military has bigger lasers, but they're potentially unsafe and not. So the idea was to integrate into the microscope column a Fabry-Perot cavity of extremely good quality to build up a 10-watt laser, 10,000-fold, to turn it into a 100-kilowatt laser, recycle the laser beam, right? One of the advantages is that the 10-watt laser is not going to cut a hole into the expensive electron microscope. And The problem, of course, is that this cavity alignment needs to be extremely good. We want an 8-micron focus at the center. The beam is going to expand so that the intensity on the mirrors is lower. That makes that possible. But the alignment of the cavity has to be so good that after 10,000 round trips, the laser beam still overlaps with itself, right? In technical terms, this cavity is very close to the edge of the stability region, and so the tiniest misalignment hurt a lot. But after years of work, we've been able to make that run continuously, in this case for 10 hours at very constant time. We have never seen a very constant phase shift. We've never seen a cavity fail due to old age. So the only way to make them fail seems to be to contaminate the mirrors. More about that later. But other than that, you can run them as long as you want. Okay. 300 gigawatts per centimeter squared is the intensity in here. As far as I know, that's the highest continuous wave laser intensity ever generated. Okay, this is what it looks like. The column at the center is a FEI Titan microscope. That's a brand name. On the left-hand side, we attach a breadboard to shape the laser beam. It then enters the microscope column here. The cavity is inside the microscope column because we wouldn't get the resonantly enhanced beam through viewports. They would just attenuate it too much, right? And then the spent beam is analyzed on that side to monitor the health of the cavity and run some feedback loops to keep it aligned. In 2019, and by the way, I should mention Osip Schwarz and Jeremy Axelrod, who are both here. They got this project to work for the first time. And so in 2019, we took these images of 20S proteasome particles and also of Rubisco particles, prepared for us by Yifan Cheng at the University of California, San Francisco. And those images, first of all, they look gorgeous. And second, we were even able to get a 3D reconstruction from them. So all is well, right? Unfortunately, all was not well. And we soon found that the laser faceplate did not live up to our expectations. This is the contrast transfer function. How much contrast do I get as function of the spatial frequency? So large structures in the specimen are here, small structures are here. The ideal CTF that we expected from our microscope is the blue dotted line, and our data, imperfect as it was at the time, was significantly below the expected performance. So first of all, what limits the expected performance? Well, unfortunately, we have to magnify the electron diffraction pattern to match the size of the electron focus to the size of the laser focus. And the extra electron optics needed for that generates extra aberrations. And so even the theoretical performance of our Titan microscope is not as good as the one as a standard electron microscope. But it wasn't even as good or as bad as expected. So what's going on here? Well, whenever an electron beam passes close to a conductor, it is subject to fluctuating magnetic fields generated by thermal electron motion inside those conductors. In simple words, the electron beam was too close to the wall, and the wall is a dirty thermal system that generates fluctuating magnetic fields. The solution to that was to increase the diameter of the hole that the electron beam has to pass as it makes it through the faceplate. And with that, we were able to get the performance up so much that it is almost indistinguishable from the theoretical limit for that microscope. So that was a success. Another thing has to be pointed out. The phase shift is very, very stable. It's around 90 degrees, plus minus maybe 10 degrees over an 8-hour data taking session. That is so much better than the best performance of the Volta faceplate before. And so we took data. Here's a serendipitous discovery of, or here's a first example how the laser faceplate shows you unexpected detail about your specimen. We were not looking for it, but these are apoferritin molecules. They look like little soccer balls, right? If you look at these things, you can see that sometimes they look like rings, hollow rings. Sometimes they look like Cs. Sometimes they look like filled rings. Sometimes they look like very incomplete Cs. That is an unexpected level of particle-to-particle variation in these specimens. This variation is likely just damage caused in sample preparation, so I'm not claiming we've made a new biological discovery here. But the interesting point is that even in the best images taken without the faceplate, this damage was overlooked because you can't see the particles individually so well, right? So even though this is not an interesting feature that we have spotted for the first time thanks to the faceplate, it is a feature that the faceplate has made so obvious that it became impossible to ignore. We've also, that was more recently, so I'm deviating from chronological order here, imaged COVID-like particles. So these are denatured COVID viruses that don't make you sick, otherwise we wouldn't be allowed to work with them. But when you look at these images, my first comment was I get sick just from looking at them. They look so nice. And we then took the images of apoferritin molecules again with our old microscope and got a resolution of 2.8 angstrom in a single particle reconstruction. And that is really the limit that we can expect to get from our old microscope because of the added chromatic aberration. So the faceplate here performs as well as it possibly can, but it has been integrated in a microscope that is not state-of-the-art by several metrics. It doesn't have how much more time do I have?
About 10 minutes.
Okay, it doesn't have high throughput specimen handling. It doesn't have the resolution of a standard microscope. So what to do about that? Thanks to the imperfect images that I showed you, we were able to get a couple of people to believe in the technology, starting actually with the Gordon and Betty Moore Foundation, and Gary might be here. So thank you. And I also hear that you have helped supporting this very conference that I'm speaking at. So thanks to that support, we've been able to set up a new microscope, which is now really state-of-the-art. I should say that this instrument is very special even without the laser faceplate. It has a electron source with extremely low energy spread to overcome the increased chromatic aberration of the faceplate optics. It has all the automation of a modern instrument that allows you to load specimens in the evening and then go home and it images them at night. It has a spherical aberration corrector that will help us to get a completely zero-free contrast transfer function if we do everything exactly right. It has custom electron optics that matches the size of the diffraction pattern to the laser beam while introducing only a minimum amount of extra chromatic aberration. And again, that extra chromatic aberration is then overcome by the low energy spread. Has an energy filter to get rid of elastically scattered electrons that contribute noise but not information, and a modern electron detector. We've built the faceplate for that. Here's a photograph of it. So you see the large beam hole. You can't see much else. We store these things inside an ultra-high vacuum chamber just to keep the dust off. So we're really paranoid about not getting dust on our faceplates. We're probably overdoing it, but on the other hand, our faceplates go to high power regularly, and so it's worth it. One day we'll find out how much you really have to do. Here's another example for dust paranoia. So when installing the faceplate into the microscope, you have to squeeze yourself into a little box with filtered air blowing on you and the faceplate dressed up in a full clean room gown. And when I asked one of the postdocs, how do you fit into this box? He said, with great discomfort. But it pays off. So here are gold diffraction patterns imaged with that microscope. I should say, no, this is a Fourier transform of an image taken of gold particles. And you can see the 0.7 angstrom diffraction ring here. So with the faceplate installed. So that shows that even including possibly dirty effects generated by installing this faceplate into the microscope. This is really surpassing our expectations. Here's some nice images of apoferritin taken laser on versus laser off with the new microscope. You can see the particle-to-particle variation again. So when we took these images, we were under a little bit of a deadline pressure because I had to give a presentation to the sponsors. And so we took only 1 or 2 images of each type of specimen and then moved on to the next because we wanted to have a gallery of what can you do with this. So let me show you this gallery. Here are ribosomes. And then we also set out to take a tomogram. Now, what's so cool about a tomogram? A tomogram shows you how the particles interact inside their native cellular environment. So you cannot just see the structure of this molecule is that, but you can see these molecules are always found close to the other molecules, or these molecules get distorted if they interact with these other molecules. And so what you do is you take a slice of a cell and image it from several aspects, right? The problem with that is that unfortunately the specimen becomes inevitably charged by the electron beam. Now that's a routine thing that occurs all the time. It's relatively harmless in standard electron microscopy, and there are ways to reduce it, for example, coat it with a conductive layer. But in the faceplate microscope, you have the additional condition that the electron beam needs to intersect with the laser beam. And so a small electron beam deflection that might be harmless in a standard microscope could make phase contrast unworkable here. And so we tried to make that happen. We developed an automated alignment procedure that essentially images the laser beam between biological imaging sessions. And from these images, we can extract the degree of misalignment between electron and laser beam, and then give feedback to electron beam deflectors to make corrections. And that has worked well enough so that we could take this tomogram. So this movie, imagine you are flying from top to bottom into a slice of the specimen. The specimen is deroofed. Yeast cells, deroofed is a polite word for essentially you make them explode. And so what you see is yeast cell fragments scattered all over. So this is not a very sophisticated specimen, but it is one that shows the workability of that. So let me see. I don't want to bore you with this movie over and over, but the filaments that you can see are actin filaments. Sometimes you see dark dots. These are probably ribosomes. And then what we've highlighted here is fragments of the cell membrane. Okay, so again, not a big biological discovery, but it shows that you can use phase contrast to take tomograms. Okay, final thing I want to mention is in-focus imaging. So what's so cool about in-focus imaging? Standard electron microscopy is done at a large defocus of maybe 0.5 micron. And the y-axis on this graph is how much information can you extract from the specimen. And if you're taking pictures, of course, you're focusing, or your camera is auto-focusing usually, because that gives the best looking pictures. And mathematically, that means in focus, you get about twice the information from your specimen than if you're out of focus. Okay, so we want to, the problem is in focus imaging can really only be done with phase contrast. So we want to image in focus to get this doubling of the information at low defocus. Of course, you can't pre-expose the specimen that you want to image in order to set the focus because of the dose limitations. So we borrowed a strategy from Radostin Danev where you determine the focus in 4 areas surrounding the area of interest. And with that, we could show that the sigma of the defocus setting is about 13 nanometers, which is the range that we need. And so we were able to take some images in focus. So here is laser off, here's laser on with defocus. and the top is laser on in focus. And in the Fourier transform, the defocused images have these dark rings that are responsible for the halving of the information integral. And those dark rings are gone when you're in focus. And in the real space images, you can see little halos surrounding the particles caused by defocus, which are absent in focus. All right, with that, go back to the title slide. Here's a plot that Peter Petrov, one of the postdocs, made, comparing the signal to noise of images with the laser on to the signal to noise of images with the laser off. If the ratio is 1, then that means the faceplate doesn't do anything. If the ratio is larger than 1, then the faceplate is better. And there's a large range of spatial frequencies over which the laser faceplate indeed improved the signal to noise by about a factor of 100 in fulfilling what Feynman wanted us to do in 1959. The new microscope is taking data again. These images were taken just the day before we drove here. And the plan now is to characterize how well does it work, perform single particle analysis and tomography with it. We're working with the Chen Zuckerberg Imaging Institute to set up a beta version of the system that could be a first kind of user facility. We're also working with Thermo Fisher to transfer the technology. And the dream is that that would make 100% of the information that is carried by the electron beam available to users. And so at the shot noise limit, so beyond the shot noise limit, give me 30 seconds for that. I should start with a beautiful paper written by my former postdoc, Osip Schwarz and colleagues, where they proposed to use image charge interactions. So the electron beam gets split into 2 conductors and induce image charges there, and that mediates interactions that lead to squeezing. And then later you can recombine the 2 beams and generate superpositions to move the squeezed quadrature to the one that you want to measure. As beam splitter, you could use, for example, the laser faceplate. Instead of image charge mediated interactions, you could also use quantum non-demolition measurements of the relative number of electrons here and here to generate a squeezed electron beam. And finally, I've been careful to say we want to surpass the shot noise limit because that is de facto what is limiting us, but not necessarily the standard quantum limit, because standard quantum limit is on the uncertainty of amplitude versus phase measurement. But if you don't care about the phase, you can use classical electron-electron calculations to get better than the shot noise limit, as is routinely done in electrical engineering, where you can generate currents with less than shot noise simply by putting a very large resistor in series to your load. With that, I want to say that I have the absolute privilege to work with both mentors, including Bob Glaser, who came up with the basic ideas, Eva Nogales, who has been helping us behind the scenes for a decade or so. She's been paying the maintenance contract for the microscope without even telling us. When I learned what it costs, oh my God. And also the very, very, very nice people in my group. Unfortunately, Julia Mohammed is just a visitor, not part of our group, but other than that, many of them are here, so keep stumm, and I thank you for your attention.
I was wondering what other methods you thought about applying this phase shift to electrons, like delay line, or what are the alternatives?
I'll give you the boring answer. We thought long and hard about how to use the laser and very little about alternative methods in order to make this took years from the first idea to even the proof of principle, and those years were spent concentrating the photons in that focal point, right? When you want to do things that take that long, you have to hyper focus on that. So yeah.
Okay, thanks. Awesome results.
Thank you.
I had a question. Do you see any kind of back action on the optical field from electrons?
That's something we did think about. So the simple answer is there are 10 to the, I don't know, 20, 24 photons in there for each electron. So it would be extremely hard to see, let's say, a first order back action. But very rarely what happens is an inelastic scattering between a photon and an electron, and that would generate a blue photon propagating down the microscope column. We've thought maybe that can give us an alignment guide, put a PMT in the microscope column looking for blue photons, but even that, even if the beam is running at full blast, we expect one blue photon every 10 seconds or so. So it's extremely, extremely big. The positive thing about that is that each of these inelastic electron-photon interactions would be a loss mechanism. It removes one signal electron from our beam. And so the fact that this happens rarely is actually a good thing.
And maybe just one more quick question. So if you were to somehow make the cavity slightly sensitive to the electrons, would you be able to use that to do your kind of QND measurement of electron number?
That's an absolutely awesome idea. So you'd have to have a cavity in the opposite regime, right? Put only a few photons inside, single photon detector. Let's brainstorm about that. That sounds very cool.
In the interest of making sure we all get a break, let's find the speaker afterwards for any further questions. We have now 15 minutes. Next session will start at 10:35. So thank you again.
Thank you.